Hello, welcome to Math 1960. This is section 301, Calculus 2, UNO summer session number 3. So today we will discuss the comparison tests. So we will discuss comparison tests for conversion and diversion. And then we will discuss comparison tests or the limit comparison test. All right. So first, let's talk about the theorem of comparison test for conversion. So suppose that you have um, a's of k, which is between 0 and b's of k for all values of k, and then the series b's of k for k equal to 1 up to infinity is a convergent series. Then the other series, which is a's of k for k equal to 1 up to infinity, must also be convergent. So in an example, now we are using the conversion test. So the conversion test. So now we want to come up with the series that is always less than or equals to this series for all values of k. So we would say 1 over n raised to power of n. This is always less than or equals to 1 over 2 raised to power of n. So this is geometric series, which is, this is always true for n greater than or equals to 2. This is always true. We know that geometric series with r equals to 1/2 is a conversion. So that means this series here, k equals to 1 up to infinity of 1 over 2 raised to the power of k is conversion. That means this one is also going to be convergent. So in comparison test for diversion, so if we have c's of k that are always between 0 and a's of k, so if c's of k diverges, then a's of k must also diverge. So let's see an example on that. So first, let's say k plus 3 over k plus 2. Let's express that in terms of n. So let's say n plus 3 and n plus 2. This is the nth term of this series. This is always going to be greater than 1, because here I'm adding 3 to the upper, to the numerator, and adding 2 to the denominator. This is always going to be equals to greater than 1. So that means n plus 3 over n plus 2 times 1 over n would be greater than 1 over n. What I did is I multiply both sides with 1 over n. This is known as harmonic series, which is diversion. So this is an harmonic series which is divergent. That means this is also going to be this series here will diverges. So we are going to discuss the limit comparison test. Suppose you have a series a's of k for k equal to 1 up to infinity and b's of k for k equal to 1 up to infinity. So these are positive, both of them have positive terms. So limit of a's of n and b over b's of n, if it's equal to L, there's a chance that both of them converges or both of them diverges. But if limit of a sub n over b sub n is equal to 0, and then we know that the series b sub k converges, that means the series a sub k would also converge. If limit a sub n over b sub n is goes to infinity, and if k equal to 1 up to infinity or b sub k diverges, then a sub k would also diverge. So now we want to determine whether this series here diverges or converges. So using the limit test, so here we're going to come up with our biggest hurdle here is to come up with b sub n. So we know our a sub n is going to be equals to n plus 1 over n plus 2. So first of all, if we say n plus 1 over n plus 2, this would always be less than 1. Then now we multiply both sides by 1 over n, so we have n plus 1, n plus 2 times 1 over n. That would be equal would be less than 1 over n. We are not going to use the comparison test here. We are using the limit comparison test. So we're going to say at this point that our a sub n is what we have here, which is n plus 1 over n plus 2. And then our b sub n would be equals to 1 over n. So then we use the limit as n goes to infinity of n plus 1 over n plus 2, and then we divide by 1 over n, so 1 over n will take care of this n. So limit of this right now, it's going to give me 1. Well, if limit is going to be 1, and then I know that b sub n here diverges, that means a sub n will also diverge. This is according to the theorem that we just discussed. Okay, using the limit comparison test, now we have a p-series. Determine whether the series converges or not. So first, we are going to say our a sub n is going to be equals to 1 over 2 here n raised to power of 3 over 2 plus 5. This is our a sub n. So our b sub n, we come up with b sub n from here, and it has to be p series. So that means when we have a big n, this 5 here will be negligible. So we're going to have 1/2 times 1 over n raised to power of 3 over 2. So now we may choose our b sub n to be equals to 1 over n raised to power 3 over 2, and then limit as n goes to infinity of 1 over 2 n raised to power 3 over 2 plus 5. So when we time it with when we divide it by b sub n, we're going to get n raised to power 3 over 2. Okay, so that means we're going to have limit as n goes to infinity of n raised to power of 3 over 2 divided by 2 n raised to power 3 over 2 plus 5. So that means we're going to have 1/2 here. So when we take the limit of this, we're going to get 1/2. So limit of 1/2, we know that b sub n here converges because it's p series. So that means a sub n would also converge. So we want to determine whether the series, this series here converges, and at this time we're going to use geometric series as our b sub n. So our a sub n at this point, it's going to be equals to 2 raised to the power of n over 3 raised to the power of n plus 5. And then these will approximately equals to 2 raised to the power of 3 n. So let's choose this to be our b sub n, because the problem prompt us to come up with some sort of geometric series. So this is a geometric series with r less than 1, which means that it's going to be a conversion. Okay, so at this point we're going to say limit as n goes to infinity of a sub n. At this point, a sub n is going to be equals to 2 raised to the power of n divided by 3 raised to the power of n plus 5 times 3 raised over 2, raised to the power of n. So then we're going to have limit as n goes to infinity of 3 raised to the power of n divided by 3 raised to the power of n plus 5. And then this should give you 1. So since we have b sub n is conversion, and then the limit is equal to some number L, that means also this this geometric series converges, and that would conclude it.